Hello everyone and welcome back to Nunley Math as we begin a discussion today about experimental probability. Experimental probability. Up until now, we've actually been dealing with something referred to as theoretical probability. Even though we haven't used the term theoretical, when we defined probability, we said it is defined as the ratio that compares the number of desired or positive outcomes to the total number of equally likely outcomes. And we used a lot of chance tools to help us with that. For example, if I were to roll a number cube, I know that a six-sided number cube would have the numbers 1, 2, 3, 4, 5, and 6 on it. So if I asked you the probability of rolling a 5, we would say, well, there is 1 5 out of 6 equally likely options, giving us 1/6 as our probability, or more specifically, our theoretical probability. And we turn that into a decimal and a percent. And we did that with a lot of things. We said if we wanted the probability of rolling something greater than 2, we would have a 3, a 4, a 5, and a 6. So 4 of the 6 are greater than 2. And we did lots and lots and lots of different examples of that over the course of a week or two in my class. But here's what I want us to think about today. If we know the probability of any single number on a number cube that is fair is 1 out of 6, or 16.7%. That means every 6 times I roll the die, I would expect to get one of each of those numbers to appear. So I thought, it might be interesting for me to test that theory out. So what I did is I went ahead and grabbed my document camera that I have here in class, and I went ahead and rolled a die, I believe 20 times, in order to see what actually would occur if I were to do that. So let's take a second and see what happens. Now, ordinarily in a classroom setting, it would have been way more fun if I had divided you into groups and allowed you opportunities to roll dice and record your results, but this is kind of the best that I could model for you in our distance learning situation. So what I did is I went ahead and rolled it 20 times, and then I went back through my video and recorded a tally chart showing what occurred each time. So you can see in my rolls, I rolled 1 1, 3 2s, 4 3s, 7 4s, 1 5, and 4 6s. In other words, my rolling gave me 1 1 out of 20 rolls. Or as a decimal, that came out as 0.05, or as a percent, 5%. And so I went through and calculated that for each side. I rolled 3 2s out of 20 rolls, so what actually occurred was 2s occurred 15% of the time. I had 4 3s, which is 20% of the time. 7 4s out of 20, 35% of the time. I only rolled 1 5, that's 5% of the time. And I only rolled 4 6s, which is 20% of the time. Notice, I was expecting to get every number to occur 16.7% of the time. But that's not actually what happened. That's not the reality of the situation. This is referred to as experimental probability. It's what happens when we actually conduct our experiment. The formal definition is the number of times the event actually occurred compared to the total number of trials. And what we find is that our experimental probability does not necessarily always match our expected outcomes. Our experimental probability doesn't necessarily match our theoretical probability. And that's because the theoretical probability deals with what happens over a long period of time. I only rolled my die 20 times. So if I had rolled this 200 times, or 2,000 times, or 20,000 times, or 2,000,000 times, what I would expect to happen is I would expect that eventually these tally marks would even out. Eventually, over a long period of time, you would see each of these fractions get closer and closer to being equal to 1/6, or 0.167, or 16.7%. Here's another example of what that looks like. I gave my son Kieran, that's him here in the picture, a 5-section spinner. You can see it's red, yellow, purple, green, and blue. And I had him spin this spinner 20 times. Now, what I would expect to happen is I would expect the probability for any of those colors to be 1 out of 5. So yellow should appear 1/5 of the time, purple should appear 1/5 of the time, green should appear 1/5 of the time, blue should appear 1/5 of the time, and red should appear 1/5 of the time. Or as a decimal to percent, it would be 0.2 or 20%. And when he spins this spinner, I would think that every time he spins 5 times, one of those would be green, one would be yellow, purple, and so on. So what I'm going to do is I'm going to go ahead and put some dots, 1, 2, 3, 4, 5 dots, down here on my graph at 0, 0. The reason for that is if he spins it 0 times, there's a 0% occurrence for every color to appear. So I went ahead and put those here into my graph. And I'm going to play part of this video, and I'm going to be pausing as we go to kind of update what the table looks like for our current results. Now you can see after his first spin, you can see that he spun a purple. Take a look at the probabilities here. The probability of purple is 1 out of 1. He got a purple 100% of his spins. That's way higher than what we predicted would happen, but in all honesty, no matter which color he hit, it was always going to be 100% experimental probability out of one roll, or one spin, because he's going to spin one time, and that one time it is going to be a particular color. What's really interesting to me is that means that all the other colors have an experimental probability of 0. It is literally impossible after one spin to get an experimental probability of 20% or 1/5, because the only option is it either did occur on that spin or it did not occur on that spin. So what I'm going to do is I'm going to go ahead and put my red, yellow, green, and blue dots down here at 0, and I'm going to put my purple dot up here at 100%. So after one spin, purple has happened 100% of the time, and all the other colors have happened 0% of the time. Let's take a look at his second spin. So his second spin was a red. Notice that now we have spun twice. One of them was red, one of them was purple, so 50% of the time I got red, and 50% of the time I got purple. Notice everything else has occurred 0% of the time. What's interesting is for experimental probability, after 2 spins, there are only 3 possibilities. Either something happened 0% of the time, or something happened 50% of the time, or it is possible I could have gotten red or purple twice in a row and it would have happened 100% of the time. Those are the only 3 options. After one spin, you only had 2 options, 0% or 100. After 2 spins, you have 0, 50, and 100. It is impossible after 2 spins to get an experimental probability of 20%. I'm going to go ahead and put those dots on my graph now. Notice that we have the purple and the red here at 50%. Everything else is down here at 0. The third spin is a blue. I'm going to do the exact same process. Notice the only possibilities now, or something could have happened 0 out of 3 times, 0% of the time, 1 out of 3, which is 33% of the time. It is possible something could have happened 2 out of 3. Maybe I spun 2 purples in a row. I don't know. 66.6% of the time repeating, or 100%. It is impossible to get an experimental probability of 20%. And our fourth spin was a red. Let me put those dots on for my last one. There we go. Notice 50% red, 0% 0% yellow, 1 out of 4, 25% purple, 0% green, 25% blue. Notice we're getting closer and closer to that 20%. Notice what's happening here. You only have 4 choices if you have spun 4 times, either 0%, 25%, 50%, 75%, or 100%. Now I know this is going to get tedious if I continue to do this for the entire video, so what I'm going to do is I'm going to let the video play, and I'm going to gradually fill in this table without pausing so that you can see the results after 20 spins. Now, I think it was important, even though I realized this was time consuming, I think it was important for you to see an actual person spinning an actual spinner and recording the results, because it's very easy for us to just make up data and tell you, oh, this is what happens, and to expect or assume you're going to believe it. But I think it's important for you to see that this is how real data looks. Theoretical probability is very convenient because it tells us the long-term outcomes, but sometimes it's useful to see that data doesn't always come out perfect and nice and neat on the first few trials. Instead, we're looking at the long-term results of spinning a spinner. In fact, if I were to look at this graph right here, notice that all the colors, no matter which color you pick, eventually is headed either downward or upward toward that 20%. Now, it's a little bit difficult to see here, so what I've done is I've gone through and I've done each of these graphs separately. This is the graph of the blue section results. Notice we had no blue, and then after 2 we finally, we had no blue, but after 3 we finally had a blue. So blue occurred 1/3 of the time. Notice that it's gradually coming down, it spikes up a little bit, and it's always, always, always moving closer and closer to this black line right here, which is the theoretical probability. Here's green. Notice we had a long time where we didn't get any greens at all, but then we had a couple that occurred pretty quickly close together. Notice that it is getting closer and closer to that 20%. Here's the purple section. Notice that purple was the first one we got, so it started off at 100%. Then we didn't get it, we didn't get it, we didn't get it, got another one. Didn't get it, didn't get it, didn't get it, got another one. You're seeing that because purple occurred first, it's starting off with a really high experimental probability. But over time, it's starting to even out more and more, getting closer and closer to that 20% mark. This should say yellow. I don't know why I left it as purple. That's a typo. Purple didn't happen for a long time. You can see we got to the 7th spin before we actually got a purple. Didn't get one for a long time, then got a second one. Notice, though, we are trending gradually upward toward the 20%. Here's red. It went up, 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 up. Then we had a long stretch where there weren't any, and then it came back down, always headed toward that, should be 20%. I've got my line drawn in the wrong spot. We'll have to go back and fix that, won't we? There's your 20% right there. Always headed toward the 20%. Now, it's interesting to me that red hasn't gotten closer than it already has. That could be an indication that my spinner isn't perfectly flat, or that there's something wrong with the spinner itself. But I would imagine more than likely it's just simply a matter of, or a result of only having 20 trials. When I put them all back together, you can kind of see that gradual trend right there towards the 20% mark. That's what we would expect to happen over a long period of time. So let's look at 4 quick examples then of experimental probability and talk our way through this. Susan spins the spinner below. There it is. 25 times and lands on purple 17 times. What is the theoretical probability of landing on purple? In theory, what we should expect to happen over a long period of time is we should expect to have 2 purples for every, let's see, 3, 4, 5, 6, 7, for every 8 spins. I would require my students to put that in simplest form, and I might ask them to put it in decimal or percent. But in reality, what actually happened in our experiment is that it landed 17 times out of 25. 17 times out of 25, which is 68%. In reality, we got a lot more purples than we anticipated. Now, that could be a result of just having a very small number of trials, or it could be the fact that there's something wrong with our spinner. In order to know that for certain, we would have to spin a whole lot more than 25 times. Important to realize, this is what we expect to happen. This is what really happens. A magician has you shuffle a standard deck of 52 playing cards and to hold them out in front of you. Little typo there. He then proceeds to draw the King of Hearts 7 times in a row, replacing the card and reshuffling between draws. What is the theoretical probability of drawing the King of Hearts? Well, there's only one King of Hearts in a standard deck of cards. If you look at our first lesson on probability, we actually talk about what a standard deck of cards looks like. So if you're unfamiliar with that, make sure you go back and watch the simple probabilities video. A King of Hearts occurs 1 time out of every 52, which is roughly 2% of the time. But the magician pulled it out 7 times in a row. He got the King of Hearts 7 out of 7, or 100% of the time. Obviously, there's a huge discrepancy between the theoretical and the experimental probability. It could be a result of only having a very limited number of trials. More than likely, if you're talking about a magician, he has some kind of trick which skews the theoretical probability in a way that we can't see. The table below shows the results of a survey that asked 50 people how many cars they own. Based on the table, what is the probability that the next person you talk to would own 3 cars? Now, this is really interesting because buying cars is not a set of equally likely outcomes. You are not equally likely to own 5 cars as you are to own 2 cars. That doesn't make any sense at all. So a theoretical probability for this story is probably not possible. Instead, we can only look at the experimental probability. In our survey or in our sample, the number of people that owned 3 cars was 9 out of a total of 50 people. 15 plus 18 plus 9 plus 6 plus 2 is 50 people. So we would say roughly 18% of the people are going to own 3 cars. Now certainly, again, 50 is a small sample size, but you are more likely to have good results with experimental probability over time with a larger sample size than with the idea that there's a theoretical probability that you could apply to this situation. Last one. If the spinner shown is spun 20 times and the results are given below, what is the experimental probability for each letter? And then I have all the letters written out. I would strongly recommend that you pause the video and try this one on your own. Again, I want the experimental probability for each letter, so this should have 4 separate answers. I'm going to assume if you wanted to do that, you already have. The probability of getting an A, well, let's see, there's 1, 2, 3, 4 A's out of the 20 letters. I would require my students to simplify that. You get 20%. The probability of a B, there we go, 1, 2, 3, 4, and 5 out of 20, or 1/4, which is 25%. The probability of a C, I'm actually going to erase my ink, and then I'm going to redraw. Probability of a C is 1, 2, 3, 4, 5, 6, 7, 8 out of 20, which is 40%. And then if that's 4, 5, that's 9 plus 8, that's 17. That means the rest of them are going to be D's, which is 15%. Hopefully this has been useful and helpful to you. Hopefully it makes sense what we're talking about when we say theoretical versus experimental. It is very common when students are being tested or assessed on this for them to mix up those two things. So just make sure that you slow down and you're reading each question extremely carefully before you begin to calculate those probabilities, because you have to make sure you get the right one. Theoretical is a prediction about long-term results. Experimental is what actually happened in the experiments. As always, please make sure you take the time to give us a thumbs up, leave us a comment if you can. Make sure you turn on those notifications by ringing that bell so you receive everything that is coming through from Nunley Math. Thank you guys so much. You take care of yourselves, all right? Bye-bye.